Here we're looking at our rules of exponents and our rules for simplifying square roots together. And remember, we'll use our rules of exponents with square roots as well. Because they're related in some way, if you think back to order of operations, the idea of Irmdas and the idea that, like addition and subtraction are related, multiplication, division are related. Well, exponents and roots are related, which is why we talk about these things together. All right, so going through our rules of exponents first here. The first one, 0 as an exponent. Anything to the 0 power is 1. And this is kind of one of our oddball rules that we just kind of have to memorize, all right? When we have something raised to the 0 power, it's a 1, all right? So if I take a look at this guy, 27 to the 0 power, well, that's a 1, all right? Anything to the 0 power is a 1. And if we look at something like this guy, 829,073 to the 0 power is a 1, all right? And then something like this guy, keep in mind, because this isn't in parentheses, the 17 to the 0 power is a 1, and then times the negative, so that's actually a negative 1, okay? And it would be a little bit different if this was in parentheses, then it would be a positive 1, okay? So just keep that in mind. Negative exponents, remember negative exponents, we flip to the other side of the fraction bar, and we make them positive, all right? So something like this guy, if I have 7 to the negative 3rd power, I just flip it. I say, hey, you know what? Right now this is over 1. I just switch it. I switch the sides, and I say this one goes down here now, and now it's a positive, all right? And this one I could continue to simplify. That's a 343, okay? If I look at something like this guy, again, instead of that being in the numerator, I just send it to the denominator. So I say that's 1 over x to the second, and I make it a positive exponent. Once I switch it to the other side, it becomes positive. And then this one, same kind of thing. I can bring the negative down with it if I want, negative 17. And notice that the 17 itself doesn't become positive, only the exponent becomes positive, all right? And that one we'll just leave like this. We're not going to plug that into our calculator. But it's something enormous and ridiculous. But again, negative exponents, to make them positive, we just put them on the other side of the fraction bar, okay? Remember, adding and subtracting terms, when we're combining like terms, we essentially don't do anything with the exponents. We leave them the way they are, all right? The idea behind combining like terms is that we add the coefficients, and the variable part really just stays the same. It stays the way it is, all right? And so when we look at something like these guys, all right, 4x squared plus the 5x squared, well, really all I just do is 4 plus 5 here, and 4 plus 5 is a 9. And then the x squared part just stays as an x squared. Because remember, I can't add these together unless they're the same thing. If one of them's an x squared and the other one's an x, I'm not even allowed to add them together. If one of them's an x and one of them's a y, I'm not allowed to add them together, all right? They have to be the same in order to add them. And after I add them, they stay the same, that variable part, okay? So I just add the numbers, the variable part stays the same. In other words, I do nothing with the exponents, all right? Here, same kind of thing, 17y to the 4th minus 6y to the 4th. Really, it's just 17 minus 6, which is 11. And then the y to the 4th just tags along for the ride as a y to the 4th. It stays the same, all right? In order to be allowed to add or subtract, they have to be the same. After add or subtract, they stay the same, okay? Same thing here. When I look at these guys, x to the 3rd and x to the 5th, I'm not allowed to add these together. They're not the same, so I can't do anything here. They have to just stay the way they are. I can't add these in any way, shape, or form, okay? So again, when we're adding or subtracting, the variable part has to be the same, and then after we add or subtract, they stay the same. We just add or subtract the numbers, the variable part stays the same, okay? Multiplying and dividing, remember when we multiply, we add the exponents. When you divide, you subtract the exponents, all right? And so as we look at this, again, that's only for exponents that we do that. The numbers that are out front, we do the same thing that we've always done. For example, if I look at this guy, 3 times 6, the numbers out front, that doesn't change. 3 times 6 has always been an 18, will always be an 18, and in this scenario, it's an 18, all right? When I look at the b values, though, when I multiply those, the rule is I add the exponents. That's going to be b to the 31st, and that's it, okay? When I'm multiplying, even though the operation is multiplication, the exponents do something special. They get added, all right? Same thing here. This is multiplication. 2 times 5 is a 10. But now the a values, when I multiply, I add the exponents. That's a to the negative 6th. But then, of course, I can also take care of that negative exponent. Again, the 10 gets to stay where it is, but I can make the exponent positive by moving that a value to the denominator. Okay? The next one, same kind of thing. Instead of having a variable here, I just have numbers. Well, that's okay. I add the exponents. That's 10 to the 15th power. And remember, that's what we do when we're dealing with things in scientific notation. Instead of having a variable, we have 10 raised to a power that all these scientific notation problems have in common. So I use rules of exponents with those powers of 10. Okay? So 10 to the 6th times 10 to the 9th, 10 to the 15th, I add the exponents. Okay? Once again, division, we subtract the exponents. So here, 10 divided by 5 is still the same. That's still a 2. But now for the a values, when I look at this, I subtract the exponents. So 3 minus 2 is a 1. And you don't have to write the 1. You can just write it as 2a if you want. If you leave the 1, that's also fine. All right, either way. If I look at the next one, 6 divided by negative 3 is a negative 2. That hasn't changed and will never change. But now when I divide the variables, I subtract the exponents. So that's going to be an x to the 8th power. Okay, subtract the exponents. And then this one, negative 2 divided by 2 is a negative 1. Once again, I subtract the exponents. So when I do y to the 4th divided by y to the 2nd, I subtract the exponents. That's y to the 2nd. Okay? And then exponents and roots. Remember, these are related. They're similar to one another in that exponents, when I raise it to a power, I multiply the exponents. And then when I take the square root, I divide the exponents. And remember, for square roots, we're dividing the exponents by 2. Remember, because there's a little 2 there. All right, we'll talk about that in a moment. So for example, when I look at this guy, again, I'm raising this whole thing to the 3rd power, so I multiply the exponents. That's x to the 30th. Okay? Here, when I raise this to a power, 5 to the 2nd power is a 25. That doesn't change. But now I multiply the exponents. That's a to the 6th power. This one, negative 3 to the 3rd power. All right, so negative 3 to the 3rd power is a negative 27. But now I multiply the exponents. That's x to the 21st. Okay? And remember, taking the square root here. When we take the square root, remember, every square root has like a little 2 right here. We don't write it, but it's always there. That's what we're dividing the exponent by, is that little 2 that's not written. Okay? So here, this would be a to the 15th. Remember, we divide the exponents. Here, this one, the square root of 81 is a 9. And then we divide the exponents. That's x to the 12th. Here, the square root of 49 is a 7. And then we divide the exponents. That's y to the 6th. Okay? So rules of exponents. Remember, anything to the 0 power is 1. Negative exponents go to the other side of the fraction bar. That's how we make them positive. And then the rest of these, when we're adding, subtracting, the variable part stays the same. When we multiply and divide, multiplying, we add the exponents. Divide, we subtract the exponents. When we raise to a power, we multiply the exponents. And when we take the square root, we divide the exponents. Okay? All right, so simplifying square roots. Remember, there's 2 ways we can do this. We can do our factor tree and look for those pairs. Or we can look for perfect squares that divide evenly into the thing, all right? And so I'm going to do 3 examples here, and I'm going to do each of them twice. One doing a factor tree and one doing the perfect squares. And so if I look at something like this, the square root of 80, if I'm doing the factor tree, I just start breaking this thing up into as many values as I can until I can't break it up any further. So like 80 is something like 2 times 40, all right? And then 40 is, 4 times 10 maybe. And then 4 is 2 times 2, and 10 is 2 times 5. All right? And the other thing that I always do is I'll extend this last branch just to make sure I can see everything written side by side. This is the prime factorization. I can see that it's, to get an 80, it's 2 times 2 times 2 times 2 times 5. It's these values right here. Okay? And so to do the square root, I just look for pairs. So I say, oh, here's a pair of 2s. So that means I can write a 2 on the outside. Here's another pair of 2s, so I can write another 2 on the outside. And the thing that doesn't have a pair, the 5, well, that stays underneath the radical, okay? And now I simplify it just a little bit further. That's a 4 root 5, okay? And that's it. If I look at the next one, same kind of thing. Let's do our factor tree. 75, maybe you break up into something like a 5 times 15, and maybe you need your calculator a little bit to divide these. You know, you can tell that it's divisible by 5, but maybe you don't know it was times 15. Well, that's okay. take your calculator and do some division. And then this is 5 times 3. And again, I'll always extend this branch that kind of got cut off early just so I can see all the numbers lined up, 5, 5, 3. And so now I look for pairs. Here's a pair of 5, so I put a 5 on the outside. The only thing left, the 3 doesn't have a pair, so it stays on the inside. Okay? If I look at this one, factor tree, here we go. The 90, maybe you do something like a 9 times 10. The 9 is a 3 times 3. And then the 10 is a 5 times 2. And now I look for pairs. Here I have a pair of 3s, so I put a 3 on the outside. And then these guys, neither of these has a pair, so they both stay on the inside. But I'm not going to leave them as 5 and a 2. I'm going to regroup them as a 10 here. I'm going to recombine those using the multiplication and write it as 10. It would be silly to leave it as a 5 times 2. Okay? So that's the factor tree. We break it down as far as we can break it, and then we look for pairs. Each pair comes out. Anything left over stays underneath the radical. Okay? Doing the same thing with perfect squares. Remember, your perfect squares numbers, like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Basically, all the numbers that we know how to take the square root of. Like any number in this list, if I said, hey, what's the square root of 16? Hopefully you would say it's a 4. If I said, what's the square root of 25? Hopefully you'd say a 5. What's the square root of 64? Hopefully you would say an 8. All right? So the perfect squares are ones that we can easily take the square root of. And so what I do with this is something like this guy. I break this up into perfect squares. I say, hey, are there any perfect squares, any numbers from this list over here that divide evenly into an 80? And I want to find the biggest one, and it might take a little guess and check using your calculator, that kind of thing, all right? But eventually you're going to find out that 16 times 5 gives me an 80. And so now what I do is I just take the square root of the stuff that I know how to take the square root of. I go, hey, what's the square root of 16? Oh, that's a 4. And really, I'm just taking the square root of each of these individually. The square root of 16 is a 4. The square root of 5, well, I don't know what that is, so I just leave it as the square root of 5. Okay? So it's really, I'm just taking the square root of each of those numbers. The square root of 16, I was just able to simplify to a 4. The square root of 5, well, I couldn't simplify. Okay? Same thing with the next guy. I look for perfect squares from that list. 25, so 25 times 3 is a 75. And then I say, hey, I know the square root of 25. The square root of 25 is a 5, right? So that becomes a 5. But then the square root of 3, well, I don't know what that is, so I just leave it as the square root of 3. Okay? And then this one, again, I'm looking for perfect squares. The perfect square divides into this as 9, so it's 9 times 10. And then I say, hey, I know the square root of 9. The square root of 9 is a 3. So I write the 3 down. But then when I try to do the square root of 10, I say the square root of 10 is, well, I don't know what the square root of 10 is. I just leave it as the square root of 10. Okay? So simplifying radicals. Again, we look for perfect squares and we take the square root of each perfect square. Or we do that factor tree. We break it down as far as it can be broken down, and then I take the pairs out. Anytime I have a pair, I write it on the outside. Anything that doesn't have a pair stays on the inside. Okay?